Okay, great. So I'm Claudia and I have Wajiha with me. We're both working for Harry, who just gave the talk about geology. And we kind of want to extend on that with now looking at the morphology of the moon more closely, so that you then tomorrow have it easier to actually map something. Okay. So we just heard we have two basic landforms on the moon, and which are the dark ones, the mare, and the lighter ones, the highlands. And both of these terrains basically share that they're heavily cratered. Everywhere on the moon we can find thousands of craters. They're just everywhere. So that's the first feature we're going to look at right now in some more detail. So on the left side, we do have an image from the Lunar Reconnaissance Orbiter taken from orbit, and to have a comparison to what we're seeing here, on the right side, it's an oblique view. So we're looking into the same crater, and some of you might run into the troubles that were explained earlier this morning, where the left side might not look like a crater, but actually more of a dome shaped. That's why if you compare these images, maybe you see more clearly that it is actually a crater. We have the view on the right side that is coming in where the arrow is pointing in the left image. And you see these central peak structures. At the center of the crater, we see the rim around the crater, which is illuminated on the right side. So sunlight is coming in from the right, creating the shadows on the right part. And then the crater wall shows this rough texture where we see this steep incline to the rim. We do see on the crater floor parts that are very, very smooth to the right, kind of where the arrow is pointing, and then more rougher parts of the crater floor on the right side, on the left side, sorry. Exactly, so this is Tycho crater, one of the most prominent craters, and we do have another crater just for comparison. Again, we have the same crater on the left and right image. We look into, on the right side, we look into from the direction of the arrow. Sunlight is coming again in the direction of the arrow. And what we see here is again a central peak, very much smaller than in the first image. However, we do see more of terraced crater walls now. So below the rim, there are several terraces built up by the crater wall. What we see also with craters is the crater ejecta, which can stretch far above the crater rim. The fresher crater is, the more crater ejecta we see, the larger crater is, the more ejecta is going to be there. And if it's very fresh, we see a very light pattern stretching out radial from the impact itself. On the crater walls, we see different structures. We have seen already terraces that build. We can sometimes see landslides, like on the right side, where we have the crater floor to the left. I marked it on there, so you might be able to see it. The arrow is pointing downwards, where the flow kind of went down the hill. You see that it stretches out into the crater. We have on the left side several different flows that reach into the crater. The crater floor is to the bottom, where you see this dark crater fill, and you see different kinds of landslides. You see blocks that come down the crater wall. All that can happen on a crater wall, as well as terraces that form by the impact. As we're dealing with very high temperatures due to the impact, we can form impact melt. And those can turn into spectacular forms and shapes. You see oftentimes floating structures in there. You see patches of it. You see that it forms sort of rills where it streams down, or and that is often within the ejecta, that it's fluidized forms of the ejecta where we have impact melt in it. We have something called fractious floors. Harry also mentioned this before in his talk, where we have a crater, and on its floor, it had been filled flat, basically, and then we see ridges in it. So on the left side, you have this Kumorov crater, and in the oblique view, you see on the right side that we have tons of grabens within the structure. We have these ridden plateaus within it, and those actually form when a plume from below, or believe that it formed when plume from below came up, and it just got short of reaching the surface. However, it bulged up the surface already, so that we now crack the floor because of the rising of the surface. We have seen already in the geology discussion that different crater sizes form different craters. So we just want to expand on that a little bit more. So the smallest craters, when you go to the left side, are simple craters, or what we call simple craters. They have a rim that is basically round. They have no obvious features on the crater floor. We do oftentimes see ejecta, and those craters are very small. So this one is about 20 kilometers in diameter. We can see slumps on the crater wall. We might see some flat floor down below, something like that. If we get to larger craters, we get to craters such as Tycho, which we saw in the very first image, where we have a simple central peak. We do see this very clear distinction of the crater rim, the crater wall, patterns within those. We see a crater floor that might be filled with impact melt, and the crater itself is much larger. As you can see, there's a scale bar 20 kilometers down below. So we're looking at much larger craters. And then going up to even bigger craters, in this example, Schrödinger crater, we do not only form a central peak, but we form central ring structures. Oftentimes these these craters are filled, and then we can only see a ring structure of elevated material around the center of the crater. And as these craters are usually bigger, we also see oftentimes more of the ejecta material. And as we go then to even bigger basins, we get multi-ring basins. In this example, Orientale, where we have not only one ring structure, but several rings that make up the crater. It is important, though, that not all these craters are going to present itself in their best shape, so to say. And as craters get older, they lose a lot of their features. So when you're mapping, you might not see these perfect examples of craters, but rather something very much degraded. If we go from right to left, we have the very young craters. Those show ejecta. They oftentimes very round. They show bright rays usually. They have this really defined crater ejecta around them. And as we get older, so Eratosthenian craters in this case, we lose the ray material, which is the first thing we will not see anymore because this fresh material will not be visible anymore. We still see the ejecta blanket. We still see that the rim is relatively great, intact, it's round. But we do not have the rays anymore. As we get older, go to the Imbrium age, as the Eratosthenian and Copernican craters are oftentimes very small, we now get to larger craters because the very small ones might not survive as long as the bigger ones. So we have oftentimes larger craters. We see still ejecta blankets, however, not as clear defined. We do still see an intact rim oftentimes. We will not see the ray material. We will have oftentimes already problems with defining the clear rim, as some parts may have slided down into the crater, have degraded already. And if we get even older, go to pre-Imbrium craters, Nectarian craters, we do not see the whole rim maybe. We do not see the ejecta, or at least very few parts of it. The older we get, we lose all these crater features. There might have been another crater impacted on the old crater, or we have landsliding. We might have some collapses of the structures. We might have filled the crater up with Mara units or something like that. So the older a crater gets, the harder it is to identify. All right, so moving on, we want to look at Mara features. You've seen before, these are the dark albedo features. They form smooth plains mineralogically. They have a higher iron content, and they mostly fill low elevation regions. We look at them, you've seen it before. We have these dark plains. Of course, they're also heavily cratered. The older they are, the more craters they're accumulated. We want to now look at some of the features we find in these Mara units. So we have pit craters, as discussed before, and one of the ways that we can identify a pit crater from an impact crater is that we do not have a high standing rim, we do not have ejecta. We might be able to see into the underground with it, so that we see that there's a hole below it, which is not typical for an impact crater. And what is very interesting, you've seen it before, we can probably see a cross-section of the lava already, the lava floors, the Mara that accumulated. That's one. And then we have the lava tubes itself. So while the pit craters penetrate within probably lava tubes, we have the lava tubes that might collapse on their own and then form these rills, or we have lava tubes that actually float over the surface and eroded away the mare below it. And these form these very nice lobate features. Another feature we see are domes. These are elevated forms on the Mara unit. We have domes which occur within a large region where the whole region is kind of elevated and has the domes on top of it, like the Mount Surunka volcanic complex, where several domes are in one spot basically, and the whole region is elevated, forming a bigger mountain region. And then we also have other regions where we have a similar dome, a singular dome. And some of them might have depressions on top. Those might be the volcanic vents. There might be craters that just happen to be on top, and we have to be very careful when looking at them. The other feature that we already saw before are wrinkle ridges. They can stretch up to several hundred of kilometers across Mare units. On the left side, you have a side view of one. You can see how it stretches far over the whole area. You see how it they connect into different wrinkle ridges. Also on the right one is a more view more from the top. It gets into sort of oftentimes into a sort of braided structure. We've seen it before, just so that you get a view from it on a different angle. Also here we have the large structure inside it where we have the wrinkle ridge going, and then several small ones which are actually flow fronts of Mare units. Those are not, and oftentimes these flow fronts are not good to see in the images you're gonna have. So if you have them, great, but wouldn't count on it, right? And then what is way more common are flooded craters. So craters that where part of the rim breached and the crater was just filled with Mare units that flooded it. So the lava went inside, filled up the crater, and what we now see are basically ghost craters where we just see sort of the rim, some of the rim that is still standing, whereas the rest of it is filled. It might be that the crater was filled all the way to the top, as in these images, or sometimes just parts of it were filled. What we know then is that the crater has to be at least older than these last lava flows, which tells us something. Another interesting feature in Mare are swirls. These are these high albedo features within the dark Mare. They form beautiful pattern. Within these Mare, we have several places where we can find swirls. Some of them very prominent, some of them less so. They do show up in these very intriguing clusters on the Mare unit. Always very high albedo on the very dark Mare. Again, we have a view from the side on the bottom right. So it's just stretched over the Mare. There's no elevation associated with the swirls, neither depression. They're just the same basic and just have a different albedo. And then something else that's really interesting are irregular Mare patches. I have trouble seeing these the right side up. So the smooth area is actually reaching out. So it's higher in elevation than the rough patches. Again, maybe you can see it on the other side of the image or the right side. The smooth parts are the ones mounting up or supposed to be mounting up. And these are very young volcanic features. They have been dated. So these are one of the youngest features on the moon, and really interesting to study. There's tons of studies going on about these, how they come to be. So great stuff. And then we have pyroclastics, which Harry also talked about. We have pyroclastics like in Schrödinger, where we have a very small spot, basically where just one occurrence for pyroclastics. And then we have Schröter Valley, where we have a lot of pyroclastics reaching over vast Providence. And the pyroclastics are darker than Mare in albedo, which is how you can identify them. And of course, these more volcanic morphologies almost never occur isolated. So you might have an area like this, and then you can identify several different morphologies within them. So we see wrinkle ridges, we see pyroclastic vents, we see volcanic tubes, we see lava flows, and have to distinguish all of them. And they're not in the laboratory where we can have just one of these morphologies. Something very interesting is dark halo craters. So we're if you look to the right, we're on the ejecta of a crater, and there are these small craters on there that excavate dark material. So they're having a dark halo, basically, excavating material from below the ejecta blanket of the bigger crater in the picture. So that tells us that we have a darker unit below the surface, and gives us an indication of how big the surface morphology is, the surface unit is, and what lays below it. Right, so another area we're going to talk about is the highlands, which are basically everything that's not Mare. These are high albedo areas. They're heavily cratered. And most of them are higher in elevation than the Mare, just because the Mare filled the lowlands, basically. And highlands can occur in different shapes and sizes. Most of the time you see some of a rough terrain. It's oftentimes hummocky. It occurs as heavily cratered very often. It shows secondary cratering, which is crater chains coming from a bigger impact crater. Or you might see higher standing massifs, something like that. We have all of these highlands are oftentimes very rough. We do have some parts, however, of the highlands that are rather smooth, like on the right side where we have the Imbrium plains. And these are light plains, which are very similar in appearance to Mare units, as they are very smooth. They have a composition, however, that is similar to the highlands, and therefore they show an albedo that is similar to the highlands. So we have dark Mare, and then we have light plains that look like Mare, except that they have the high albedo of highlands. Right. And just so to summarize these linear features we might run into on the moon, we have rills, such as this one right here. We have basically lava tubes. Within the Mare units, we have these wrinkle ridges, which are very large features most of the time. They can form smaller ones, but as you see here, they run into each other. They occur due to the compression of the unit. And then we have these scarps that can be found on highland material, also sometimes where we have these this steep scarp face, and then the back hill that is not as steep and just more not as steep. We have a more steady incline on that side. Right, so looking at some of the scarps, we have here some images. We have the scarp face that is illuminated here on the left side, where the Rupes gauchi name is across to, and then it stretches very far over the surface. As also on the right side, we have the lobate scarps on the floor of a crater. Again, we can see the scarp face very clearly. And then generally just something about the data types we might run into while mapping. We have the albedo information. So the moon is very gray. So we basically have only albedo information on how dark or light something is. Now, then we have the topographic information telling us something about the elevation on the ground, which also is very helpful in identifying units. And then on top, as a last step, basically, we have the spectral information, giving us more insight on what we're looking at. However, as it only penetrates the surface, it might be very dangerous to only look at spectral data. So we take the high resolution image data, basically most of the time just first looking at this, then adding the topographic information where we get elevation data, and then take special high resolution derived information, such as we can create slope maps from the topographic informations, or we might have a rock abundance information. Something like that might help us in the long run on creating our map. And then we go into mapping. We identified different features based on all the data that is available. We may take into account our image data and map on the base of that. And if we go deeper into it, I think Harry had that as well, where we have Mare units, but if we look at the spectral data, we might be able to identify more than one Mare unit, whereas if you only look into the image data, this Mare might look all the same. So we have just, as if we had just one giant Mare unit, but looking into the spectral data, we actually see, okay, all these different colors represent different compositions. And then just very general things to keep in mind. We have, for all craters, basically, they have an ejecta blanket, which is usually larger than one diameter of 1 times the diameter of the crater. And the basic principle should always apply that younger units overlay the older ones. So it cannot be that a unit that is older than the younger unit cross-cuts that unit, because the younger unit will always be on top. And then if you create a map, you have to check that your contacts are logical. Lava will not stop flatly on a blank surface. It will flow probably, and that should be represented in your map. Okay. And that's all I've got. I saw that there's a lot of blinking, so I guess there's something in the chat, but I don't know how to access that while I'm talking.
Yes, Claudia, thank you for your beautiful talk. Very clear from all the features and how to interpret them, and even the overlapping and cross-cutting relations at the end. So there were actually several points, questions that were partly answered already. So there were questions about how swirls were formed or are formed, and the sinus rails are formed. So, but yes, they were actually answered already. So in the chat. So by Caroline and others. So if there are other questions, but just to make a summary to the one that are not looking to the chat, spheres are thought to be formed by remnant magnetism that deflect the solar wind. So since solar wind, I would say, make darker the surface by weathering, we have this effect of different weathering at the surface due to these solar wind deflections. But how these magnetic fields are associated to a given feature or another is not well defined yet, and even their formation is still a little bit debated. Then there were another important question was about sinusoidals, that it was already answered by Caroline, that they are volcanic features, and their origin is related to lava flow channels, or eventually underneath them we may infer lava tubes, in particular if we have skylights there. There are some linear rills that actually are related to emplacement intrusions of dikes, so of lava that is intruded within fractures and solidify. So this is just a summary of the chat. Are there other questions about Claudia?
There was a question kind of earlier, farther up in the chat about how the different periods of the lunar stratigraphy are defined and divided. I was just trying to find a figure to show the lunar stratigraphic framework. I haven't found it yet, but maybe one of you would like to say a few words. I just said in the chat that it's defined by the Nectaris, Imbrium, Eratosthenes, and Copernican craters as boundary units, but the Copernican period actually extends a bit older than the Copernicus crater itself, which is about 850 million years old. The Copernican period starts at about 1 billion years ago because it's defined by whether you can still see the crater rays or not. So I don't know, Claudia, maybe we could just go back to your slide that shows the 3 different type of ages of craters.
Sure.
And so getting information about how your geologic units fit into this framework is first achieved by looking at the relative ages of your units that you've defined, the relative age to these classifications of craters that you also have in your area. But then you can also get an absolute age determination, which isn't the advanced course on the lectures on Wednesday evening, and then the practical on Thursday morning of how to derive ages by actually measuring the crater size frequency distribution.